In this session we'll explore a few more properties of the angular momentum operators, the absolute angular momentum L squared and the z component of the angular momentum LZ hat. And particularly in terms of their reflection properties or parity, like for example, if you switch in the expressions for these operators, you know them from earlier sessions in terms of sines and cosines and so on of theta and phi and exponential phi. You have expressions for these operators in terms of those r, theta and phi. So you can make these substitutions, these reflection properties, if you like. So you can change r, the r vector, position vector, into minus r. You can switch the theta to pi minus theta, or phi to phi plus pi, and so forth. These various operations. And I ask you to do it for homework. So you'll find that under these reflection operations, you find that the L squared and LZ as operators don't change. It just it just comes out of the mathematics. So I ask you to do that. Okay. So if you call these operations p hat, so they're like parity operators, if you like. And if you apply p and then L squared, and you get the same thing as if you did L squared then p, because the p doesn't make any difference, then the commutator of p, these parity operators, doing this or this or this, so the commutators are 0, right? So the parity operator p commutes with L squared, and the parity operator commutes with LZ, right? Now you know from earlier theory that if you have two operators and they commute, that means their eigenfunctions are the same. Those two operators have the same set of eigenfunctions. Okay, so you can say then that the angular momentum eigenstates, in other words, the eigenstates of this and this, which are the same by the way, because remember these two commute. Okay, so the angular momentum eigenstates are also these parity operator eigenstates. Okay. Like for example, the phi in the spherical harmonics, you had a theta term and a phi term. Well, what's the parity for the theta? Sorry, the phi term. Well, if you switch phi to phi plus pi, so you've got a phi here, so make it plus pi, and you will then get Im phi as usual here. But you've also got this pi, so then you'll get e to the Im pi. Well, e to the pi I is minus 1, so to power m, so you get minus 1 to power m. So the parity, if you like, of the phi term is minus 1 to the m. So if m is even, the parity of this term is plus or even, and if m is odd, then the parity of this term is minus 1 or odd. Okay, that's just what's saying here. Now, for the associated Legendre polynomials, with your two parameters L and M, have a look at the expressions we've had earlier for this, and I ask you to do for homework. Find the parity for the ALP, associated Legendre polynomials. Okay. And you'll find that it's this. So do that for homework. You'll be substitute these Legendre polynomials depend on theta. So see if you can get this expression for the parity of the associated Legendre polynomials. Homework exercise. All right. Now this little bit here, well, the rest of this session is effectively just revision. It's sort of a repeat for what we did pretty much in Appendix B. Okay. Now the eigenstates for these two angular momentum operators they have a theta component and a phi component. Now the phi component was of this form, if you remember, because we chose this z component because it's so simple. Because its differential operator was easy, it was just effectively d by d phi. Whereas the theta, its term was a bit more complex. So the eigenstates for these operators will just be a product of these, the theta term and the phi term. And we've done that before. So here's your theta term, here's your phi term, and you just it's just a constant here used to normalize this eigenstate, this wave function. Now, it has two parameters, two eigenvalues, L, or actually L times L plus 1, are the allowed eigenvalues, the eigenvalues of L squared, the operator L squared. And your M, they're the eigenvalues of the operator LZ. Okay? And the eigenfunctions of both those operators are the same because they commute. Two operators commute. Okay, so this is just a normalization constant such that this wave function, which you write this way, usually capital Y, which is by definition a spherical harmonic. Okay? So the eigenstates of the two angular-momentum operators with a given eigenvalue L and given eigenvalue M, so you can write it as a ket in the direct notation this way. Okay? And it's it's this, which but this is a spherical harmonic, right? So you can write it this way. So there's like three ways of writing it, and you can solve for the normalization factor here, just a number. Okay. Now these spherical harmonics, just a note added here. They are not unique to quantum mechanics. Right? The angular momentum component of quantum mechanics. They pop up in all kinds of other places. For example, wave theory. Perhaps you might see it. I don't know if you can see the top line of the next session. Potential theory. If you're trying to calculate the potential at various points in space of a particular object, for example, that might be charged, but it has a certain unusual shape. So what's the potential at different points at a distance and a different angle, orientation, theta, phi, from that shape. So potential theory uses these spherical harmonics as well. So it's not just quantum mechanics. Okay, so next session I'll just go straight on with a bit more discussion about linking the eigenvalues M with the eigenvalues L.